Okay, thanks. So this is joint work with Peter Burgester, Ankit, Michael Walter, and Avi. And yeah, alternative minimization, or as Bernard said, which should be the title of the paper. Really cool matrix stuff. So I'll start basically explaining the really long title, I guess. So the title goes here. So the introduction, I'll explain to you alternative minimization, give you some context. Then I'll proceed to talk a little bit about invariant theory and how that comes into play. And I'll talk a little bit also about scaling algorithms and our setting and our results. OK, so the problem setup. So your input in alternative minimization is usually I give you a function and some domains x1 up to xd. And this function takes value over the reals. And your goal is to find a global optimum, x1 star up to xd star, right, such that it minimizes the function f over this domain. Now, notice that I'm not usually requiring anything about the function or about the domain in general. But the only constraint that we have, for example, the domain doesn't need to be convex. And for the purpose of this talk, it won't be, as you will see. But usually, the nice thing about the setup is that minimizing f in each of these blocks. So if you fix, let's say, if you just take x1 and you fix all the other blocks, your input in all the other blocks, minimizing f in each of these blocks is simple. So for example, if you fix any coordinate and you just optimize over this coordinate I here, your function is simple. OK, I'll give you some examples now in the next slide. So, oh, sorry. I'll tell you what alternating minimization is, right? So since you know that minimizing in each coordinate is simple, let's just do the obvious, right? Let's just fix all the other coordinates, find the minimum, and keep improving things. So repeatedly, we're going to solve this basic problem on the different coordinates. So we start with the initial guess, and then at each time t, pick a coordinate, find the infimum, and update just that coordinate, and fix everything else, and just keep going. And hopefully, after some time, you're very close to your solution. OK? And now, examples of this abound in many areas of science, not just computer science. For example, the famous Lemke-Hausen algorithm to find Nash equilibrium in two-player games, where you start with some two initial strategies, and then you fix one strategy, and then you find the best response, and you keep going to try to find the Nash equilibrium. And this is shown to converge, but we know it was shown later to converge, and we know it takes exponential time. In statistics, Cisnar and Tusnadi, they gave the example that Bernard mentioned, which I give you two convex sets in Rn, and then they try to find the distance between these two convex sets. So you start with the initial points in each of the convex set. You fix one. You reduce to a convex optimization problem. Then you try to find the minimum, and so on. And Sinkhorn in '64, he defined this matrix scaling problem, where you pick up some non-negative matrix, and you try to scale this matrix to become doubly stochastic, which, again, is another example of alternating minimization, where you just make the matrix stochastic, like row stochastic, and then you mess up the columns. And then now you say, OK, now let's make it column stochastic, and so on. And there's generalizations to quantum information theory. Like Bernard said, the quantum operator scaling is also another example of alternating minimization. And well, since I'll be in the job market soon, machine learning as well, they use a lot of alternating minimization in matrix completion and block coordinate descent, which is block coordinate descent is essentially alternating minimization, right? You fix some coordinates, and then you optimize over the rest. So remember just the fourth one next year or so. So OK. Now, what is our aim among all of this world of alternating minimization? OK? So our aims are the following. So we want to develop techniques to prove, oh, sorry, if I go back, for a lot of these, for the first two bullets in game theory and statistics, it was people didn't know efficient convergence. They could only prove convergence of this method, but they could not prove efficient convergence. And efficient convergence was only proved very recently. And 3 and 4, we are very interested in proving efficient convergence. Okay? So our aim here is to develop techniques to prove efficient convergence of alternating minimization procedures in the algebraic setting, which I'll explain in the next slides. And also, we want to generalize these techniques to other settings of optimization problems, which I'll talk a little bit about later. And well, ultimately, we also want to build more connections to other areas of math and science. As you can see, there's plenty, but we want more. So to describe the algebraic setting in which we're going to talk about alternating minimization, let me just talk a little bit about invariant theory, which is a beautiful theory. It started by Cayley in 1840-something. And now it's really beautiful, and I'll describe a little bit now. So suppose that you have a vector space V, and G is a group that acts linearly on it. So if you pick an element of the group, and you act on V1 and V2, the action is the same as G acting on V1 plus V2. And so here's some examples. Suppose that V is the complex numbers, and then you have the group is the symmetric group that you just permute the coordinates. Okay? So that's one group action. And some other group is you have the group of matrices with complex entries, and your action is SLN by SLN, which SLN is just all the invertible matrices, okay, with determinant 1. And this acts by changing basis, right? So this is a group action that we're all familiar with. And an invariant polynomial is simply a polynomial in the vector space, which doesn't change by the action of G. So if I give you a polynomial P, P of x is equal to P of gx for any G in the group. So for example, in the case of the vector space being the complex space and the symmetric group, the invariants, we all know they're generated by the symmetric polynomials. And in the case of the change of basis, we also know that the invariants here, they're just generated by the determinant. Okay? So these are polynomials that have geometric meaning. And the invariant polynomials are one of the main objects of invariant theory, studying invariant theory. And another goal of invariant theory is to understand the orbits of each point on the vector space V. And what is an orbit is essentially you pick the point V, and the orbit will be apply all of the elements of the group on this point V, and see the set of all points that you can achieve. Okay? But this is not algebraically very nice. So usually what we do is you take the orbit plus its limit points, okay? And we call that's the closure of the orbit. And it's just the orbit with the limit points in the Euclidean setting. And this can be characterized as the zero of polynomials vanishing on all of these points in the orbit, okay? So, but you can simply think of it as the orbit plus its limit points. Now, what are the basic questions in invariant theory? They're the following. Given a vector space and a group G acting on it, well, we want to compute the generators of the invariant polynomials. And we want to find relations among these generators. We don't need to be like just the basis. And we have many more. And this is only on the polynomial part, on the algebraic part. Now, with regards to the orbits, some things that we want to know about is this orbit closure intersection. So if I give you 2 points, okay, in this vector space, do their orbits intersect? That's one. That's the orbit intersection. Are they in the same orbit, right? You want to know. But more in particular, you also want to know if the closure of their orbits intersect, okay? And for example, many problems that we're familiar with, they can be stated as an orbit closure intersection. So for example, graph isomorphism is one of them, right? The group is the vector space, and the action is the symmetric group. Okay, so that's graph isomorphism. And Moumoulet in 2012, he used this GC geometric complexity theory approach to try to say, can we separate VP from VNP in this algebraic setting? This also becomes a problem of orbit closure intersection, which is the orbit closure of the determinant under linear actions is the permanent contained in the orbit closure of the determinant, okay? So that's Moumoulet's approach. And in 1965, Mumford said that understanding this orbit closure intersection is equivalent to understanding the invariant polynomials, okay? So there's a deep connection between these two. And in particular, a very basic case of the orbit closure intersection is the case where one of the points is the 0 point, okay? So then it becomes this problem. Given V in the vector space and 0, we want to know if 0 is in the closure of the orbit of V, okay? So if you take W equal to 0, you get this point. And this is what we're going to study now in this talk, okay? It turns out that this can be stated as an alternating minimization setting. So here's our question. Null cone problem. Given V in the vector space is 0 in the closure of the orbit over G. So there are ways to solve it. Well, by definition, what you can do? You can just find a sequence of elements of the group which make V go to 0. Right? That's by definition. And in 93, which is 1893, Hilbert said, it's important to notice, Hilbert said that to solve the null cone problem is equivalent for you to just find generators to the invariant polynomials and just test if V vanishes on all of these invariants. Okay? So just find the generators and test if V vanishes all of them. If it vanishes, then you're guaranteed that there exists such a sequence. Okay? And now in 1979, Kempf and Ness, they proved this non-commutative duality, which I'll explain in later slides, for any group action. It's a very general theorem. It's amazing. This generalizes Forster's theorem in many ways. So there's lots of hidden connections to computer science. So what they say is, well, look at the group. Okay? And suppose that you can take derivatives. Well, you have a Lie group, for example. The minimum of this program, so essentially 0 is in the orbit closure. Look at the norm of all the vectors in this orbit. Okay? Now, the minimum is attained when the derivative along the group action on any point in this orbit is 0 in all directions. Right? There's a similar thing. You have a convex set. The minimum is where all your derivatives is 0. Okay? Now, what they say is, well, check how close you are to satisfying this condition of the gradient being 0, and then you're at the minimum. Okay, so this is another way of solving the null cone problem, which I'll describe a little bit later. Okay, I know it's too many words, but now breathe deeply and bear with me because I'll just have to explain to you our setting. So our setting is the following. We have this tensor scaling problem, which, if you're familiar with the operator setting, we generalize the operator scaling setting. And the setting is the following. Suppose that X is, for now, a 3-dimensional tensor. Okay? And you can write X as, just by rank 1 tensors. And now the group G is the group SLN cross SLN cross SLN, let's say. So all invertible matrices of determinant 1. And this group, it acts on this vector space, on any tensor, in a very natural way, right? So A1 acts only on the first side, A2 acts on the second side, and A3 acts on the third side. So this is what we call a scaling of X. Okay, scaling of X is just this multiplication. And now the function is, if I give you a tensor X and some group element A, let f of X just be the L2 norm of this scaling of X. Okay? Now, our goal is, given the tensor X, find a star that minimizes the norm of the scaling. Okay? You can see that it looks very much like an alternating minimization setting, right? Because I have x1 is Cn1, x2 is C to the n2, and x3 is C to the n3. And then you have the group act. Oh, sorry. X1 is SLN n1, x2 is SLN2, and x3 is SLN3. And I want to minimize some function, right? And the null cone problem, on the other hand, is just to test if this infimum is actually 0. So we want to test if capacity is 0. Now, what's the connection to the quantum setting here? Well, a tensor is nothing more than a pure quantum state in many particles. And you can write it as just a PSD matrix with dimension n1, n2, n3. And the trace of this matrix is 1. Now, if you let rho of I be the marginal rho with respect to particle I, this is just it's just essentially if you think of probability, is essentially just what you would see, the statistics of each particle if you ignore the rest, okay? It's essentially the same thing as the regular marginal for probability distributions. And we have this definition that rho is tristochastic, or for physicists, locally maximally entangled, if the local statistics of the particle I is essentially the maximally entangled state. Yeah. So now one important question for them is this quantum distillation question. So given a pure state rho, can I scale this rho to obtain a tristochastic state? Okay? Can I obtain from rho a state where it's maximally entangled for everyone. And formally, this question is translated exactly into a scaling question, okay? So given a state rho, I just want to find these invertible matrices such that this scaling is tristochastic. Now, is there a connection to this? And yes, the connection is the quantum distillation is given a pure state, can we scale such that all of the marginals are tristochastic? And the null cone problem, remember, is given a tensor x, which is a pure state, is the capacity equal to 0. And Kempfness, if you just state this theorem in our tensor setting, they have this non-commutative duality, which shows that given any tensor, if the capacity is not 0, which means that if 0 is not in the orbit closure, then we can actually scale x, the pure state x, to the tristochastic state, okay? And this duality turns the null cone problem into a scaling problem, because now, given a pure state, I just want to try to scale this problem to the tristochastic state, okay, as opposed to trying to find the infimum in the orbit. And the scaling algorithm is simply this alternating minimization algorithm. So if I pick a quantum state, I just look at each particle at a time. Let's say we go cyclically, and then we say, OK, let's make this particle like just stochastic. And then I keep doing this, OK? So, and then we have an analysis in the paper, which I don't have much time to describe. But let me go to our results and some conceptual contributions. So the first result is, given a tensor x, OK, in many with many sides, where each entry is an integer with bit size b and some parameter epsilon, we give a deterministic algorithm which runs in time polynomial n b and 1 over epsilon, which outputs either x is in the null cone, which means either the orbit closure of x contains 0, or y is a scaling of x such that the distance of y to this d-stochastic state is less than epsilon, okay? So, but to fully decide this null cone problem, it turns out that we actually need this epsilon to be exponential in n. Okay, we need the epsilon to be really small. So therefore, to decide the null cone problem here, we just give an exponential algorithm for this problem. But in general, if you have a promise problem, then we can solve it. If you promise that you're really far from double stochastic, then we can actually decide it. So, and the second contribution is we give an algebraic algorithm that solves the null cone problem with deterministic exponential size. Okay, and the algorithm is quite simple. We compute all the invariant, a generator to all the invariant polynomials, and then we just evaluate x on all of these polynomials. Before, the algorithm to compute all the invariant polynomials could only be done in double exponential time, and we just make it into deterministic exponential time now. Now, in the minute that I have left, let me just say the conceptual contributions and what I wanted to take out of all of this myriads of notation. So tensor scaling is essentially an algebraic framework for alternating minimization algorithms, okay? It generalizes operator scaling algorithms, and it uses symmetry and tools from invariant theory and analysis into solving this problem. And it connects optimization and invariant theory in both ways. We're using invariant theory to solve an optimization problem, but we're also using these optimization techniques to try to solve problems that are fundamental to invariant theory and to algebraic complexity as well, okay? So what we want to say is we want to expand this use of numerical methods into the algebraic setting. Can we use more of these numerical settings to, for example, solve the PIT problem? Okay, is the PIT problem an instance of this null cone problem? We don't know that yet. But if it is, can we use numerical methods to solve them? And on the optimization side, the capacity is a geodesic convex problem. And what does that mean? It means that, well, it's not really convex if you talk about the Euclidean metric. But if you move to the hyperbolic metric in the space of matrices with determinant 1, then it becomes this geodesic. It's convex along every geodesic. So can we extend and improve these techniques that we have now to the geodesic convexity setting? Can we solve algorithms in this setting? Or can people from that work with geodesic convex programming actually give us more tools to try to solve such problems? Okay? And open questions, well, the usual. Can we have a polynomial time algorithm for tensor scaling? Can we have better algebraic algorithms? Because right now, It's really hard to compute the generating polynomials and more applications and yeah, other applications for algebraic problems. So thank you.
Any questions? Yes.
I'm not quite sure I understood in result 1 where you say there is a deterministic algorithm with this running time. Is that deterministic algorithm the alternating minimization algorithm?
Oh, yes, sorry, yes. There is the deterministic algorithm is the alternating minimization. We provide, yeah, so the main result is we provide an analysis of the alternating minimization algorithm. Exactly, that's the main, the algorithm is not new, it's just the analysis that is new, yes. Yeah, thank you.
Does the remark imply that this alternative minimization needs exponential time?
Yes. This is also showing that the alternating minimization needs exponential time as well, based on this remark. Exactly. Yeah.
So, the open problem, you have to come up with some new algorithm.
Yeah. So okay, good. So the question is, okay, this is the alternating minimization. The remark shows that we need exponential time for this alternating minimization, but and then he's saying, well, the challenge is to come up with a new algorithm, but. As I mentioned about the geodesic convexity of the problem, right? The algorithm is already ready for us to kind of, if you try to just use geodesic gradient descent, for example, then this is the algorithm that we want to analyze now. Is that algorithm better? Can we analyze this gradient algorithm for solving this problem under this new metric, right? So we need to develop this. Yeah, so we already have a candidate algorithm, but any other algorithm would be good as well. Yeah.
So in sort of more standard convex optimization, when people provide proofs like alternating minimization, they typically use some global, function properties, and this sounds like you're doing something more fine-grained. So what are sort of the crucial properties of the problem that you use to prove convergence?
Good, yeah, so I put that under the rug because of the 20 minutes. But so the idea is, right, so we want to minimize capacity, right? So what we show is that we show a global lower bound on the capacity, okay? So we show that either the capacity is 0, okay? Or if the capacity is not 0, if the infimum is not 0, right? We show that the minimum norm is lower bounded by some inverse exponential quantity. And that's what we use as our potential function. We use actually what we want to minimize as the potential function, okay? And actually, because we're solving this dual problem, right? We want to find, instead of finding the vector of minimal norm, we find something that it scales to close to d stochastic. We use the capacity, and we say the capacity is really small. And then if I'm really far from being d stochastic, every time that I operate, I'm actually exactly.